Swayam Prabha. Digital India. Educated India.
Welcome back to this course of hydraulic engineering. This week we are going to cover basics of fluid mechanics. This is the second week of this, so we call this basics of fluid mechanics 2. The first topic in this series is going to be fluid kinematics, and yes, we can proceed. So, first we will talk about the velocity field. What actually is this velocity field? You know it from beforehand, but to brush up your concepts, we will go through it once again. So, it's actually the fluids can be assumed to be made up of infinitesimal particles, and they are tightly packed together, and this is implied by the continuum assumption. So, infinitesimal particles of fluids are tightly packed together. Thus, at any instant in time, a description of any fluid property such as density, pressure, velocity and acceleration may be given as a function of the fluid's location. So, that is the basic assumption, that is the basic thing that we are going to start with, that these properties such as density, pressure, velocity and acceleration can be described as a function of fluid's location. So, this is quite important to start with, the fluid location, and properties such as density, pressure, velocity and acceleration. Okay. So, this representation of fluid parameters as function of spatial coordinates is termed as field representation of the flow. Spatial coordinates, so that is with respect to the space, so in terms of x, y and z. For example, the velocity here can be written as u is a fluid velocity or the fluid speed in I direction, I is x axis, plus v in j direction, j is y axis, and w in k direction, and each of u, v and w can be function of x, y, z and t, each of those, this one, this one, this one and this one here. Okay. So, as I told you, u and w are u, v and w are x, y and z components, okay, u, v and w of the velocity vector. By definition, the velocity of the particle is the time rate of change of the position vector for that particle. So, the velocity is the time rate of change of the position vector for that particular particle. This you already know. So, there is one figure here. As you look into the figure, x axis is in this direction, y axis is in this direction and z axis is in this direction. The position of the particle A, so A is our particle here, this one and this one. So, these particles are the same particle, but at two different times, at time t and at time t plus delta t, and this red line here represents the particle path. Okay, let me just see if I am able to do the, yes. So, this one here is the particle path. So, the position of this particle is given by the position vector, this which r of a, r a at time t, this is the position vector, and here at time t plus delta t, this is r a at time t plus delta t. So, I will go back here. So, this is the position vector at time t, and this is the position vector, different position vector at time t plus delta t. So, considering the particle is moving, so particle has moved from this point to this point via this. So, time derivative of this position, let me take out the ink first. Yeah. So, the time derivative of this position gives the velocity of the particle. So, time derivative of d r a is given by d r a dt by dt is equal to v a. So, velocity at point A, or is the same thing what I have written, okay, and which is given on the slide as well. So, by writing the velocity of all the particles, we can obtain the field description of the velocity. So, if we write the velocity of all the particles in the system, we can obtain the field description of the velocity vector v as this. V is equal to v as a function of x, y, z and t, using the equation described in the previous slide. Since the velocity is a vector, it has both a direction and a magnitude. This is the basic concept that you know from before. The magnitude of v is given by modulus of v under root u square plus v square plus w square. This is simply nothing but the speed of the fluid. So, assuming a particle has a velocity here, this is the, let us assume two direction, this is x and this is y. So, there will be a component and this is cos theta. So, the speed will be mod of v. So, if this is, let us say u1 is the x component of the velocity and v1 is the y component of the velocity. So, modulus of v in two directions will be u1 square plus v1 square. This you already know. Okay. So, now there are certain descriptions of the flow. The two most famous are Eulerian and Lagrangian. So, we will revise that as well. What is the Eulerian flow description and what is the Lagrangian flow description? So, as I told, there are two general approaches in analyzing fluid mechanics problems. The first method is called Eulerian method. In this case, the fluid motion is given by completely prescribing the necessary properties as a function of space and time. Okay. So, pressure, density, velocity, whatever properties you have, even acceleration are prescribed by describing them as a function of space and time. From this method, we obtain informations about the flow in terms of what happens at fixed point in space as the fluid flows through those points. So, this is very important. So, this is the main difference between the two descriptions. In Eulerian flow description, we describe the flow properties in terms of what happens at fixed points in space. The observation is also taken from the fixed point in space. Suppose we define a coordinate system from beforehand and all the things are observed from the So, this is x, this is y and this is z. So, if we put our observer here, for example, anywhere, it does not necessarily need to be at origin, and if we keep on observing, suppose a particle is moving like this, if we keep observing from here and we see what is happening at this particular point, at a fixed point here, the flow description property is Eulerian in nature. Okay. Good. So, a typical Eulerian representation of the flow is shown by the figure, this one, which involves the flow past an airfoil at an angle of attack. This is just to show Eulerian representation. This is flow past an airfoil. You see, this is the foil, this is an object, and this is the flow properties or the contours that are there. So, the way we have described it as one of the observer at a fixed point in space, this is Eulerian in nature. The pressure field is indicated by a contour plot showing the lines of constant pressure with grey shading indicated the intensity of the pressure. Okay. So, this is the flow and this is the pressure contour, you know. So, just want to make it very clear that all these results have been observed and obtained from previous experiments. So, this is just to show how we describe these Eulerian velocities, for example, or the pressure in this case here. Now, what is Lagrangian flow description? So, the second method called the Lagrangian method here involves following individual fluid particle as they move about and determining how the fluid properties associated with these particles change as a function of time. So, the key component is following the individual fluid particles. So, our frame of reference is fixed at one of the particle that is moving. So, that means it could be a non-Newtonian frame of reference. Earlier we had a fixed, in Eulerian we had a fixed point in space from where we were making the observation about a fixed point. Here we are following an individual fluid particle. So, our frame of reference x, y, z is at the particle itself. So, whatever motion we are observing is relative to that particular particle, and this flow description is called the Lagrangian method, and this is observed as of this particle as a function of time. That is, the fluid particles are tagged, or tagged means just putting a marker on them, or identified, and their properties are determined as they move. Okay. So, just to summarize again, the difference between Eulerian and Lagrangian flow descriptions is that Eulerian description is a description taken from a fixed point space. However, in Lagrangian flow description, the frame of reference is fixed to a moving particle. So, the difference between, as I said, the two methods of analyzing fluid flow problems can be seen in example of a smoke discharging from a chimney. I'll just okay. So, talking about 1, 2 and 3 dimensional flows. Generally, a fluid flow is rather complex, 3-dimensional and a time dependent phenomena. Any fluid flow in real life is all the three. It is complex, 3-dimensional and time dependent phenomenon. That means the velocity will be a function of time. It will have a velocity component. So, this is time dependent, means as a function of time. 3-dimensional means it will have x, y and z. All the three components would be there as indicated by this equation. V as a function of x, y, z, we can be written as u is the velocity component in x direction, v is the velocity component in y direction, and w is the velocity component in z direction. So, I, j and k are the unit vectors in x, y and z direction. From your maths class, you would already be knowing that modulus of I is 1, modulus of j is 1 and modulus of k is also 1 if we write the vectors here. So, This is just a basic revision. So I, j and k, by multiplying I, j and k, we do not change the magnitude but just try to show the direction. Rub this. So actually in almost any flow situations, the velocity field contains all the three velocity components u, v and w. In many situations, the three-dimensional flow characteristics are important in terms of physical effects they produce. Okay. For these situations, it is necessary to analyze the flow in its complete three-dimensional character. So for many flows in nature, three-dimensional flows actually are very, very important, and therefore we need to analyze in all the three directions. That is why u, v and w all are important. The flow of air past an airplane wing provides an example of a complex three-dimensional flow. How? Because aeroplane is moving, so the velocity will be changing also in time, and also because the plane is also moving, the velocity will also be a function of x, y and z. At different point the velocity could be really different. In many situations, one of the velocity components may be small. This can happen anywhere. For example, suppose there is a large tank and there is a flow in x direction and the tank is infinite in the y direction, and in that case, in one of the directions, if we don't give the speed in y direction, that component is going to be very small. So but just going back to it other than the example, the main part here is that in one of the velocity components may be small relative to the other component. In such situations of this kind, it may be reasonable to neglect the smaller component and assume two-dimensional flow. So as I would repeat again, we have talked that all the flows in nature are three-dimensional, but some of the flows can be assumed to be two-dimensional because one of the component would be very small in comparison to the other two components, and therefore we can say that this is a two-dimensional flow. In this case here, where we have written V is equal to U I cap plus V j cap, and we have neglected W cap because here it might have happened that W is very, very small than U comma V. Okay. And here U and V both here are functions of x, y, and of course it could be a function of time as well, right? It is sometimes possible to further simplify a flow analysis by assuming that two of the velocity components are negligible. So we saw that one component was negligible, but there can be situations where two of the flow velocity components are negligible, which would leave the velocity field to be approximated as one-dimensional flow field, that is V is equal to U I cap. This means that V and W are very, very small than U. So this is one-dimensional flow. In reality, such flows can be there, but it has to be very properly experimentally controlled. But in general, as I said, that the velocity is three-dimensional in nature. All right. So we have talked about some velocity descriptions now, Eulerian, Lagrangian, and then we talked about three-dimensional flow, two-dimensional flow, one-dimensional flow. Now it's time to talk about steady and unsteady flow. So as you know from before, probably from your fluid mechanics class, steady flow and unsteady flow, the main distinguishing component here should be time, right? How? That we are going to see. So one classification of the flow is steady and unsteady. In steady flow, what happens is the fluid flow conditions at any point do not change with time. This is very important, do not change with time. For example, if the velocity component, if velocity is v, pressure is given by p and density is given by rho, so the derivative with respect to time is going to be 0. There is no change in velocity. This means that the change in, let me just go to the laser pointer, the change in velocity here with respect to time is 0. Same is the case with the pressure. The change in pressure with respect to the time here is equal to 0, and the same fate is for the density. The change in density with respect to the time again here is 0. Okay. So, here and here. Okay. So, in steady flow, streamline, path line and streak lines are identical. We will, so this is actually streamline, not streamline, sorry for the typo here. Path line and streak line are identical. This we will tell you in upcoming slides, that what exactly are streamlines, what is path line and what is streak line. Good. An unsteady flow, unlike steady flow, the flow parameters at any point changes with time. That is, any of the flow properties, either it is velocity, so del v by del t will surely not be equal to 0. That is the definition of, or any property, even del acceleration by del time is not equal to 0, or del pressure as we saw, or density, del rho by del t is not equal to 0, and del p by del t is also not equal to 0. Okay. So, we have seen steady and unsteady flow. Now, we are going to see uniform and non-uniform flows, the definition of the uniform and non-uniform flow. Uniform flow. The flow is defined as uniform flow when the flow field, that is the velocity and the other hydrodynamic parameters, do not change from point to point. So, in a steady flow it was not changing with respect to time. Here these properties should not be changing with respect to the space at any instant of time. So, uniform flow is the one where the fluid properties do not change with respect to the space. For a uniform flow, the velocity is a function of time only, that is it, which can be expressed in Eulerian description as v as a function of v of t. So, v is not a function of v x, y, z, t, but only v is a function of v of t. So, these x, y, z components vanish when it is a uniform flow. Implications: for a uniform flow, there will be no spatial distribution of hydrodynamic and other parameters, as we told, because the parameters really does not depend upon the location. Okay. Any hydrodynamic parameter will have a unique value in the entire field, irrespective of whether it changes with time. Okay. Therefore, now we have two parameters here, space and time. Time was with, if something depends upon time, it will be unsteady. If something does not depend upon time, it will be steady, right. So, combining the steady and unsteady with uniform and non-uniform, we can have either unsteady uniform flow, which means the velocity will be the only a function of time, or actually it might not even change with time as well. This type of flow can be called as steady uniform flow. So, the flow properties are neither going to change in space or with respect to time. Okay, good. Now, non-uniform flow, when the velocity and other hydrodynamic parameters changes from one point to the other, it's exact opposite of uniform flow. So, the properties in uniform flow were not dependent on the position of the particle or from in this respect to the space, but non-uniform flow, it will change from one point to the other, and such flows are called non-uniform flows. These are the some of the terms that we would be encountering again when we start doing the open channel flow, for example. That is why it is important to go through it once again. Now, important points are, for a non-uniform flow, the changes with position may be found either in the direction of flow or in the direction perpendicular to it. So, if so, we have said that for a non-uniform flow, the particle properties or the fluid particle properties changes with position. So, position or the direction can be infinite, but generally it is a customary in fluid mechanics to calculate the changes in two directions. One direction is the flow direction. Flow direction means, for example, the river flows say in one direction, okay, x direction. Then we will calculate the changes of the properties in the direction of the flow. In our case, it is x direction and the direction perpendicular to it. So, suppose there is a river flowing like this and our coordinate system is x and y, for example. This is two dimensional space. So, the best way to calculate the changes is in this direction and this direction perpendicular to it. Good. So, non-uniformity in a direction perpendicular to the flow is always encountered near solid boundaries past which the fluid flows. We will come across it later in our lectures, that how near solid boundaries this velocity component changes, and that is one of the main reasons why near the solid boundaries we need to calculate the changes, and thus they introduce non-uniformity in the direction perpendicular to the flow. Okay. So, if suppose an example is there is a plate, the fluid will be flowing like this. So, there will be velocity here, but this plate is at rest. We will come to it later as well, but since the fluid is flowing across this and this is at rest, so the particle adjacent to it will try to be at rest as well, or the particle nearest to this plate will be at rest, correct. Here the velocity is suppose v of the river, I mean the stream velocity, here it is 0. So, as you can see, during this distance the velocity goes from v to 0. Good. All right, then nice. Reason, as I was telling you before, for the the earlier point that we said, all fluids possess viscosity. Sorry, I will use the pen. All fluid possess viscosity. Viscosity in a layman's term or in a old term can be said as friction in fluids, for example. And because of the friction, this reduces the relative velocity of the fluid with respect to the wall to 0 at solid boundary, as I was telling you, and this condition is called as a no slip condition. And because of the no slip condition, there is a non uniformity of the flow in the y direction. Now, what is a streamline? In a fluid flow, a continuous line so drawn that it is tangential to the velocity vector at every point is known as streamline. Okay. So, what is the streamline? It is a continuous line such that this line is tangential to the velocity vector at every point. So, if you draw such a hypothetical line, this is called a streamline. Suppose if the velocity vector is given by in I direction as u, in j direction as v, and in k direction as w, better to write it like this: u I cap plus v j cap plus w k cap. Okay. Then the differential equation of the streamline, this you have already done before, but I will straight away go ahead and write the equation is dx by u is equal to dy by v is equal to dz by w. So, this is the equation of the streamline. All right. So, now we will end this lecture with this practice problem. First we will finish this practice problem and then finish it. The question is, in a flow the velocity vector is given by 3x I cap plus 4y j cap and minus 7z k cap. This means the u component is 3x, y component is 4y and z component is minus okay, I will just use the eraser, minus 7z. Now the question is, determine the equation of the streamline passing through a point M, where M is given by 1, 4, 5. The procedure is very simple. We have done this equation before. The equation was, the equation of the streamline is given by dx by u is equal to dy by v is equal to dz by w. This we have seen in the last slide. Okay, this is the most important equation, and we already know u, for example. So, we can write as I wrote before, u is 3x, v is 4y, w is 7z. It's very important to note that we must be writing these components, whatever things we know from before. When we start solving a problem, we should be writing it down first. For example, u is equal to 3x we have written, and so on. Okay. So, this equation can be written as dx by 3x is equal to dy by 4y is equal to minus dz by 7z, because z was minus 7z. Let me take away this ink. Now, the procedure is, we will solve this one at a time. Dx by 3x is equal to dy by 4y, and secondly we are going to solve this too. Okay. And when we integrate, the first equation can be written as ln x by 3 is equal to ln y by 4 plus ln c1 dash, where c1 dash is a constant. And how do we obtain this c1? That we will talk about it next. So, in other word, we can simply write, because all these are ln, we can write y is equal to c1 into x to the power 4 by 3. Okay. All right. And on integrating the second equation, as I told, this one here, dy by 4y is equal to minus dz by 7z. Okay. So, either we can do integrate this equation, the second, or we can also use this equation, these two equations together. So, in this practice problem, we have taken dx and z. Okay. So, this gives ln x by 3 is equal to minus 1 by 7 ln z plus ln c2 dash, where c2 dash is again a constant. So, we can get simply z is equal to c2 divided by x to the power 7 by 3. Okay. So, these are the two equations that we got, correct. Now, we need to obtain c1 and c2. What is the way? We have said, find the equation of the streamline which passes through a point M, where the coordinate of M was given, x was 1, y was 4 and z was 5. This also means that this 1, 4, 5 should also be satisfying this equation and this equation, and on substituting in y in this equation we can get C1, because y here is 4, so that is 4, and x was 1, so we have put 1 here. In this way we get C1 is equal to 4. Similarly, using 1 4 5 and putting it into z equation here, again C2 can be written as z multiplied by x to the power 7 by 3. Z is 5, right, so this is 5 here, and x was 1 again, and this gives C2 as 5. Okay. So, the streamline passing through M can be given by y to the power 4 x to the power 4 by 3 and z is equal to 5 divided by x to the power 7 by 3. So, this is the problem where we saw how to solve the streamline equation, and this is enough for today. So, we will resume in the next lecture. Thank you so much for watching.